Now we've considered non-standard temperatures. The next thing that we need to do is consider non-standard conditions. So when we're talking about H naught and S naught and G naught, we're talking about systems where the concentrations of all the substances are 1 mole per liter and the pressures of all the substances are 1 atmosphere. But of course, that's not always going to be the conditions that we use for a particular reaction. So the next thing that we're going to look at is how we determine the delta G for non-standard pressures and temperatures. Now, this is going to be the equation. We're not going to derive this equation. This is the equation that we're going to use that gives the relationship between the delta G at non-standard conditions and delta G naught. So when we want to calculate delta G, it's going to be our delta G naught, so the delta G at standard conditions, plus RT ln Q. So this term here is going to take into account the change on Gibbs free energy due to the non-standard conditions. Q, you'll recall from our equilibrium unit, is our reaction quotient. So for a reaction of A going to 2B, if I want to calculate the K value, it's the concentration of B squared over the concentration of A. And you'll recall that for a reaction that's not at equilibrium, the expression is called Q. Okay, so this relationship will handle any concentrations of reactants and products, whether or not the system is at equilibrium. Now, if you look at this, when we're at standard conditions where everything is 1, we would have ln of 1 here, and ln of 1 is 0, so that's why this term is 0 at non-standard conditions, and it's just equal to G naught. Now, the other thing that we can get from this is using our knowledge of the fact that when a system is at equilibrium, the Gibbs free energy is equal to 0, and the Q is actually equal to K. Okay, we can set this relationship equal to 0 and plug in a K for the Q. And what we actually are given is a relationship between Gibbs free energy and the equilibrium constant. Okay. And these two graphs here give you a relationship between the free energy of the system at a particular moment in time, depending on whether we're equal to K or Q, okay, and the extent of the reaction. So here, this is for a non-spontaneous reaction. This is our 0 point where Q is equal to K and we're at equilibrium when our Gibbs free energy is equal to 0. Okay, at this point here, after here, we're not at equilibrium and Q is greater than K, so we've got more products in the system. Before this point, we've got more reactants in the system. Okay, and you can look at the same relationship here where we've got Gibbs free energy increasing. Same thing, we've got a 0 point. Okay, above here, we've got more products than reactants. Below here, we've got more reactants than products. It just gives a good visual. Now we can also look at the relationship between the equilibrium constant and Gibbs free energy. When the equilibrium constant is greater than 1, as you know, that's a situation where we favor the products. And so Gibbs free energy is negative. Okay, the products are favored over the reactants. When K is equal to 1, okay, the products and reactants are equally favored. And when K is less than 1, the delta G is going to be positive and the reactants are favored at equilibrium. Okay, so let's look at what kinds of calculations we can do with these relationships. Now I'm just going to change these values because I did my calculations using these values instead. Okay, so delta G naught, we're studying this reaction of 2NO2 in equilibrium with N2O4. And we've got a system where we've got 0.20 atmospheres of NO2 and 0.1 atmospheres of N2O4. And we're being asked whether or not this system is at equilibrium, and if it's not, which direction must it proceed? So in the past, we did this kind of a calculation after being given the equilibrium constant, and we would compare our equilibrium constant to our reaction quotient, and we would make a decision as to which direction the equilibrium needed to shift. We can do that same thing using Gibbs free energy. So we're going to calculate the Gibbs free energy from the tables by taking the Gibbs free energy of the products and subtracting the Gibbs free energy of the reactants. And we find a value of negative 5.31 kilojoules. Now, this is delta G naught, but this is the value that we would have if the pressures of both of the gases were 1 atmosphere. We've got the pressures at 0.2 and 0.1, so we need to calculate delta G for that particular system. So we're going to use the formula delta G naught, plus RT ln Q. Now the R value that you use is 8.314. The R value is in joules per Kelvin per mole, so we need to divide by 1,000 to put it in kilojoules. The temperature, I'm going to assume that it's 298 because it's not given. And then I'm going to take the ln of Q, which is the products over reactants raised to their coefficients. Now I just need to take a moment and double check the calculation that was done here. Okay, so this is plus 2.27, so it's equal to negative 3.03. Now, when we look at this here in the next question, we're being asked, well, in the overall question, we're being asked if the system is at equilibrium. So we know it's not at equilibrium because delta G naught is not equal to 0. And what we need to do is look at which direction it needs to shift. So in order for it to reach equilibrium, delta G naught needs to equal 0. So really this needs to get larger. So our RT ln Q needs to increase. For the RT ln Q to increase, what we actually need to happen is we need the like R and T are constants, so we need ln Q to increase. Okay, so what that means is that we need Q to increase. So in this case, the reaction needs to shift left. Sorry, no, it needs to shift right, sorry, because we need Q to get bigger, so we need the products or the value here to increase, so we need the reaction to shift right. In our last problem here, we're being given a KSP value, and the KSP is given for silver bromide, and it's given to have a value of 7.7 times 10 to the negative 13. And we can use that to calculate the delta G for the process, because delta G naught is equal to RT ln of K. Again, the R value is 8.314 divided by 1,000. We're talking about delta G naught, so that's the temperature of 298. And the equilibrium constant value is 7.7 times 10 to the negative 13. Okay, and we found a value of 69.1 kilojoules. Now for the R value here, you could calculate it using joules, so you could leave it as 8.314, and what you'll find is that you just get 69,000, so you just get a larger number, and then you can convert it to kilojoules. Again, I made my decision based on the fact predicting or knowing that delta G, it tends to be a large value and tends to be reported in kilojoules. So that concludes our lesson in free energy. Okay, there are a few key relationships that you need to know. Okay, the delta G is equal to delta H minus T delta S. Okay, and the two equilibrium formulas, so delta G is equal to delta G naught plus RT ln Q. And for a system at equilibrium, delta G is equal to negative RT ln K.